So in the last video, we talked about how we can use the derivative to figure out when a function is increasing, decreasing, or flat. And it's not super interesting, and you probably got bored about halfway through, but hopefully I showed you a few techniques that were useful for you and kind of set up the foundation for what we're doing in this video, which is far more interesting and a little bit more difficult. I kind of alluded to it at the end of the last video, but the basic idea is we're going to redo all the analysis that we did on the graph in red with the graph in blue. So for red, we were interested in flat, increasing, and decreasing. And what we saw is that flat, increasing, and decreasing corresponds with a height of 0, a positive height, and a negative height for the graph in blue. But what about the point at which f prime of x, the graph in blue, is flat? What about this point in green right here? What's its significance to the graph in red? Well, to understand that, what we really want to do is think about when the graph in blue is increasing. In this case, the graph in blue is increasing everywhere to the right of 3. F prime of x is increasing from 3 to infinity. It's flat right here in 3, and everywhere to the left of 3, f prime of x is decreasing. That's easy enough to see when you stare at the graph in blue, but that's hard to see when you stare at the graph in red. Before we think too much about what this means, in the last video, we first looked at the graph and kind of approximated where the graph in red was increasing, decreasing, and flat. And then we were like, but you can't always trust a graph. We should probably calculate this algebraically. Let's do the same thing in this video. It appears that the graph in blue is increasing when we're to the right of 3 and decreasing when we're to the left of 3. But are we sure about that? Are we sure that at 3 itself, the graph in blue is flat? Well, we could figure that out if we knew the slope of the graph in blue. And here's where things get really difficult, because the graph in blue tells you the slope of the graph in red. And what I'm asking you about is the slope of the graph that gives you the slope of the graph. The graph in blue tells you the rate of change of the graph in red. And what we're now asking about when we talk about flat, increasing, and decreasing is the rate of change of the rate of change. Really, these questions are referring to the second derivative, the derivative of the graph in blue. The graph in blue is the derivative. To figure out when f prime of x is flat, what we have to figure out is when f double prime of x equals 0. In much the same way that to figure out when the graph of f of x was flat, we had to figure out when f prime of x was equal to 0. To figure out when a graph is flat, you figure out when its derivative is equal to 0. And if the graph you want to know about is the derivative, then it's the second derivative that has to be equal to 0. What's the second derivative? Well, I don't know, but it's easy enough to calculate. I got the first derivative up here. So to figure out the second derivative, I take the derivative of this thing. I got two terms, so first we'll take the derivative of the first term, x minus 2 squared. I bring the 2 down in front, and I leave the x minus 2 alone, and my new exponent is a 1. And then I multiply that by the derivative of the inside stuff, conveniently just equal to 1 in this case. And then for my second term, I'll leave the constant of negative 2 alone, and then take the derivative of x minus 2. The derivative of x minus 2 is just equal to 1. So I get that f double prime of x is equal to this mess, which I can clean up a little bit. I can write this as 2 times x minus 2 minus 2. No reason to leave these parentheses in here, so I get 2x minus 4 minus 2. In other words, 2x minus 6. F double prime of x is equal to 2x minus 6. If I want to know when f double prime of x equals 0, all I got to do is take 2x minus 6 and set it equal to 0. Add 6 to both sides, I got 2x equals 6. Divide both sides by 2, and I get x equals 3. F double prime of x equals 0 when x equals 3. Oh, right, that's this point right here where the slope of the graph in blue is equal to 0. Because the second derivative function is easier, it's a linear function, it's a lot easier to figure out when it's increasing. To figure out when it's increasing, I just got to take f double prime of x and set it greater than 0. F double prime of x is 2x minus 6, so if I solve this inequality by adding 6 to both sides and then dividing both sides by 2, I get x is greater than 3 as my solution for when f double prime of x is greater than 0. Oh, right, my derivative is increasing over here when my second derivative is greater than 0. Again, from 3 up to infinity. And I probably don't even need to do it for you, but for completeness sake, when the second derivative is less than 0 is when 2x minus 6 is less than 0. So 2x is less than 6, so x is less than 3. My first derivative is decreasing when my second derivative is less than 0, which happens over here from negative infinity to 3. And you're like, yeah, all right, I guess that's cool that we can do the same analysis on the graph in blue as we did on the graph in red. But what did that analysis that I just did in green here about the second derivative tell us about the graph in red? Like, our original question was all about the graph in red. The only reason I'm showing the graph in blue is so that we can do analysis on the graph in red. Well, I'm not just wasting your time. The second derivative of a function tells us about the shape of the function. What does it tell us? Well, think about what this means. The second derivative of x is the rate of change of the rate of change. If the second derivative of x is greater than 0, that means the rate at which this function is changing is increasing. The slope of the tangent line to the graph in red at this point right here in 3 is -1. How do I know it's -1? Because the height of the graph in blue is -1. F prime of 3 equals -1 at this point. What if I take a step over here to the right? What if I think about f prime of 4? Well, that's going to be equal to 0. Why? For two reasons. Because the slope of the tangent line right here is 0. The tangent line is horizontal. Or because the height of the derivative right here is equal to 0. What if I take another step over here and consider the derivative at 5? Well, I need to know what is the slope of the tangent line to the curve at this point right here. And I could estimate that by looking at the graph in red, or I could get an exact answer by thinking about the height of the graph in blue, which is 3. So f prime of 5 equals 3. Maybe we'll do this one more time. What if I go all the way over here to 6? And I want to know about f prime of 6. That's the slope of the tangent line to the graph in red over here at 6. The graph in red is really steep here. It's going up really quickly. This is going to be a large positive number. How large? Well, I can figure it out by looking at the height of the graph in blue, which is exactly equal to 8. So f prime of 6 equals 8. What if you think about how these derivatives are changing as I go to the right? They go from -1 to 0 to 3 to 8. They're getting larger. They're increasing as I go to the right. What does that mean for the shape of the graph in red? It means it's going to kind of curve upwards as we go to the right. The word we'll use for that is it's concave up. On this interval from 3 to infinity, the graph of f of x is concave up. For concave up, think about like a bowl kind of. It has this shape. Contrast that with over here from negative infinity to 3, everything to the left of 3, where f of x is concave down. The shape of the graph in red kind of looks like an upside down bowl, kind of looks like this. It'll take a while to get comfortable with this, but this shape over on the left side of our graph is fundamentally different than this shape over on the right side of our graph. And we can talk about that difference by considering the second derivative of the function. Wow, that's a lot of information. Let me try to tie some of those concepts together. First of all, we figured out that the second derivative of x is equal to 2x minus 6. The second derivative, just like the first derivative, just like the function, is itself a function. We can graph 2x minus 6. 2x minus 6 is a line, it's a linear function that has a y-intercept at -6 and a slope of 2. So I go up 2 units each time I go 1 unit to the right. Up 2 units each time I go 1 unit to the right. Up 2 units each time I go 1 unit to the right. If it wasn't hard enough to look at the graph in blue and red next to each other, try looking at the graphs of red, blue, and green all next to each other. That will be the end point for this section. We want to be able to look at the graph in green and the graph in blue and use its qualities to describe the shape of the graph in red. Blue, being positive or negative, tells us whether red is increasing or decreasing. Green, being positive or negative, tells us whether blue is increasing or decreasing, which tells us whether red is concave up or concave down. Wow. Okay, I know this is getting really complicated, but maybe before I end this video, I can give a real world application to try to explain some of these concepts with increasing, decreasing, concave up, and concave down. So pretend that this function in red models my dog's position. And when I say my dog's position, I mean over time. So on the x-axis here I have time, and in the y-axis I have position. So the way the story goes is we go to the park. And often when you're talking about applications, negative numbers don't really make sense. So kind of ignore this part of the graph for now. We're going to start our graph right here and our story right here at time 0. At time 0, I let my dog off the leash at the park. My dog's really excited, loves to be off the leash, and goes running away from me. After one, maybe these are minutes, my dog is pretty far away from me. Maybe these units are hundreds of feet. After 1 minute, my dog is 500 and some feet away from me because my dog went sprinting in the other direction. But my dog's feeling a little bit guilty. If you compare how fast my dog is running away from me here with how fast my dog is running away from me here, you might see that my dog was running much faster here than my dog was running here. Because my dog's feeling a little bit guilty about running away from me. In fact, 2 minutes after I let my dog off the leash, my dog's not running away from me anymore. My dog paused, kind of looked back at me, felt a little bit guilty, and even started walking back towards me. Right? 3 minutes after I let my dog off the leash, my dog is closer to me than my dog was 2 minutes after I let him off the leash. 2 minutes after I let him off the leash, he was almost 700 feet away from me. But 3 minutes after I let him off the leash, he's only 600 feet away from me. He's feeling guilty, he's coming back to me, and he continues to come back to me until 4 minutes after I let my dog off the leash at this point right here. At this point, my dog is closer again to me, just a little over 500 feet away from me, but then my dog sees a squirrel. And my dog's paused at this instant, kind of looking back at me and looking over at the squirrel. My dog knows he's supposed to come back to me, but the allure of the squirrel is just too much, and my dog starts slowly walking towards the squirrel. And when my dog starts walking towards the squirrel runs away, and as the squirrel runs away, my dog gets more and more excited and starts running after that squirrel and is running away from me faster and faster and faster as I go to the right here. In the context of my dog and position, what do the derivative and the second derivative represent? Well, the derivative is a little bit easier to talk about. The derivative, the graph shown in blue, describes the rate of change of the graph in red. So anywhere the derivative is positive, my dog is running away from me. And anywhere the derivative is negative, my dog is coming back towards me. And anywhere the derivative is 0, my dog is paused, neither walking away from me nor walking towards me. But what about the second derivative? The second derivative is talking about the rate of change of the derivative. To understand that, compare this point right here with this point right here. At both of these points, my dog is running away from me. At both of these points, the first derivative is positive. But at this point, my dog's running a lot faster away from me than my dog is at this point. Even though my dog is going away from me at both of these points, he's running away from me here, or maybe he's just walking away from me here. The rate at which the position, the graph in red, is changing is decreasing. We're going from running to walking. And that rate continues to decrease. I go from running to walking to standing still. And it continues to decrease even more. Running away from me, walking away from me, standing still, walking towards me. But then there's this point right here where things change. To the right of this point, my dog is still walking towards me for a little while, but the speed that he's walking towards me is getting slower. He's walking towards me slowly. He's walking towards me really, really slowly. He stopped walking towards me. He sees the squirrel. Now he's walking away from me slowly, walking away from me a little bit faster, running away from me, sprinting away from me. If the function gives us position, then the first derivative tells us the change in position. In other words, the speed or velocity. The second derivative tells us the change in velocity. What is the change in velocity? Velocity is the change in position. So what's the change in velocity? The change in position. What does that possibly represent? It's the acceleration. In the example where the function gives position, the first derivative gives you the velocity and the second derivative gives you the acceleration. At this point right here, my dog's velocity is positive, meaning my dog's running away from me. The distance between us is increasing. But my dog's acceleration is negative. He's going from running away from me to walking away from me. The speed at which our position is changing is decreasing. Compare the interval from 0 to 2 with the interval from 4 to 6. On both of these intervals, from 0 to 2 and from 4 to 6, the distance between me and my dog is increasing. The velocity is positive. But what's different is the acceleration. From 0 to 2, my dog is slowing down. From 4 to 6, my dog is speeding up. The function is concave down when my dog is decelerating. The function is concave up when my dog is accelerating. And that all works as long as you're really careful with velocity having a sign. What I mean by that is when my dog is walking back towards me, we think about his velocity as a negative number. We think about my dog speed over here somewhere is 5 miles per hour, for example. My dog speed when he's running back to me is -1 mile per hour. My dog speed over here when he's running away from me is again positive, like 5 miles per hour. I don't know if that helped any, that example. Hopefully that helps tie these concepts together a little bit. If you're pretty confused right now, frankly, I'm not surprised. I think this is really confusing. But what I'm going to do in the future videos is just try to define some things more concretely and give you lots of examples to hopefully make this make more sense to you.